a few years ago in this question. And then integrating modern and fossil data, I think, is an important thought as well, that people are able to draw together information from modern organisms and adaptations and try to integrate with fossil data as well. And so I'll just give a couple of examples. Forgive me, I forgot I was going to talk about this as well. With the tools, with the trees, with the timescales, with the integration of data and the availability of new statistical methods, it's possible for us to treat fossil taxa in the way that people would treat living taxa. We can represent aspects of morphology and function and explore the way those change through time. So in a study a few years ago with Steve Brusata, then a master's student at Bristol, we were looking at the origin of dinosaurs and how from the late Triasic to the early Jurassic, I should really flip these figures, the morphospace has changed. So here we're exploring novelties, morphological characters. And this seemed to suggest, contrary to some previous ideas, that the rise of the dinosaurs did not drive out this other clade. So we were trying to use this method to explore biotic replacements, these events that we can document through geological time. At this point, dinosaurs appeared, other groups disappeared. How did that transaction happen? Did the dinosaurs kill off the other group or not? And we believed we'd found evidence here that they did not. This is an example of looking at disparity, which is the amount of morphological variation. And these tree diagrams, maybe these are a bit small, forgive me. These are to try to compare possible outcomes of comparing diversity and disparity. Here, I mean by diversity, number of species, biodiversity. And we know how to try to document that through time. We use the term disparity in the sense of morphological variety. It can be measured from shapes of leaves or skulls or whatever you're interested in, or in our case, we've often done it from cladistic data sets. But in both cases, and I'm sorry that this is a little small, there is an important question of whether diversity and disparity are coupled. As diversity increases, disparity increases, or whether they are decoupled, meaning that they change in an unconnected way. So if they are coupled, we would expect change through time to be fairly similar for disparity and diversity. And the branching tree would look something like that. New species arise and the amount of morphological space increases in a fairly regular fashion. So here, disparity and diversity are coupled. In these cases, they are decoupled. In the first case, diversity increases fast, but disparity does not. So the tree continues to occupy a fairly narrow range of morphology. In this case, disparity goes first, and the clade expands rapidly in terms of morphology, but not in terms of diversity. And then, for the rest of the time, species fill up the space without changing terribly much. So that was quite an important question to explore. And most studies so far have shown that, in fact, disparity and diversity are decoupled. This was not something we expected, but this is something about the way radiations happen. So I'll hop past this because I've gone on quite enough. And so I'll just finish with a couple, no, let that go. Diversification, yes, so functional disparity, this is a new way of, I don't know if this is completely defensible, but the disparity I was talking about was simply shape. We do want to know something about function. So Phil Anderson and Emily Rayfield and colleagues at Bristol have tried to develop ways of distinguishing functional characters from shape characters and trying to explore how those evolve through time. These are some examples of theirs looking at lower jaws of fishes through the Devonian. Forgive me, I won't explain it in detail. Another approach that is now feasible with phylogenetic trees is to explore diversification shifts. This is the idea of trying to find times when rates of evolution were very fast or very slow. And methods for these calculations had been developed quite a while ago for use on molecular trees, but they're now being made available for use with deep time trees and can accommodate extinction. So we did a study in 2008 where we were trying to identify times when dinosaurs were evolving fast. And most of these times of fast evolution, 13 of them, happened early in the evolution of the group. And there was very little after the middle Jurassic, which was quite a surprise because diversity of dinosaurs was increasing quite substantially in the Cretaceous. But this seemed to suggest that there were no particular dramatic bursts of evolution. And others have used these approaches on exploring evolution of mammals, trying to point to times of particularly rapid evolution. And they also use these comparative phylogenetic methods to explore evolutionary models. So this comparison by Supias and colleagues, published last year, was exploring the relative rates of evolution of therapsids and archosauromorphs during the Triassic. This, I guess, is the end Permian extinction, origin of dinosaurs somewhere here, and the Triassic somewhere here. And by comparing the characteristics of the evolutionary trees with different kinds of evolutionary models, they suggested that both of these trends, both of these changes in body size, were probably following a kind of passive model. So this is all very new for paleontologists to be trying to think about these things. But it allows us to be a little sharper in the way we define things like Cope's rule and trends and other concepts of that kind, which have been a bit loose and a bit ill-defined up until now. So my final slide, and I do apologize for speaking too long. My final slide, I think, then, is to try and summarize under the heading of tree thinking what has changed, I think, since the paleobiological revolution in Chicago. The one thing that they did not do, that Gould and Brown and Sapkowski and others did not do, was to think about phylogeny or trees. So all they did was in terms of paleodiversity, which is good, it's a start. But I've tried to show you some examples of disparity, functional disparity, morphometric approach, and modeling rates and modes of evolution. These are all the things that Simpson talked about in 1944, but we can now do them. And thanks to a combination of having available, for certain groups of organisms, very good phylogenies, having much improved geological dating, better understanding of how to combine those, and the availability of phylogenetic comparative methods to play with those data and try to discover aspects about rates and modes of evolution. So I'm sorry I said far too much, and I'm sorry I said it all in English, but thank you for your good attention.